This is the Do's and Don'ts of HSS webinar. A few housekeeping items about muting, asking questions, getting your PDH certificate. And then we were on this screen. So if you're licensed in Florida, Maryland, North Carolina, and/or New York, we need your license number to issue your certificate. And you can send this to us in the questions widget or email us at the address on the screen. If you are registered in those states, you are required to complete a quiz, and that link will be emailed to you at the conclusion of the webinar, and you must complete that within 24 hours of the conclusion of the webinar. PDF handouts are included in your GoToWebinar control panel. You can download them directly from there, and you will receive links in the follow-up email after the presentation. And finally, the presentation today is being recorded. We encourage you to visit our website and take advantage of more valuable information we have for you there. And with that out of the way, let's get started. Over the years, the Steel Tube Institute has fielded thousands of inquiries about the proper specification and design of HSS members and their connections. We have selected a few of our favorite do's and don'ts, and we will share them throughout the course of the webinar. While none are as obvious as the cartoon here about don't catch your pants on fire, we think you will find them equally as useful. Now, in your handouts, you have 2 extra cartoons. We added these for your amusement, but that means your PDF slides will be 2 slides ahead of mine here on the screen. A few of the learning objectives that we will cover today are: do understand the subtleties between available material specifications. Don't always rely on the full length of your weld. Do know how to avoid end distance reductions or how to apply them. Don't minimize wall thickness necessarily. Lightest is not always cheapest. Do check availability of shapes and materials. You can use STI's capability tool for that, which we will talk about later. Don't over-tighten bolts if you're using through bolts, and we'll talk about other common connection issues as well, and many, many more. The way we've laid out the webinar today is that the first half will be devoted to sharing our real-world HSS practical do's and don'ts. We will go through these in a checklist-style format. Then we will continue with a section devoted to how and when to best use HSS as part of the big picture of steel construction. And we'll wrap things up with a handy summary table to help as you design your next HSS project. So let's jump into these practical do's and don'ts. We will start with material grades and specifically A500. A500 is the most commonly used HSS material grade. Do specify grade C when you're looking at A500 material. Don't specify grade A. It's important to note that in the past, the A500 spec had 4 different grades, A, B, C, and D. And in the beginning of 2021, grade A was eliminated from the ASTM A500 spec because it wasn't being produced and it had a low yield strength. So that left grades B, C, and D. Be aware that A500 carries dual certification. What that means is that for the past 20-ish years or so, all domestically produced materials have met grade C and grade B. So a lot of engineers are still specifying grade B as a minimum because it had a lower yield strength, but we are recommending not to specify grade B. You're getting grade C anyway. You see an image here on the screen of the dual certification, the material test report, and it shows that it is certified to both grade B and C. So you're getting grade C steel even if you specify grade B. So it's best that engineers design more efficiently using the higher grade C yield strength because you're getting it anyway. So we recommend that you do that and take a look at your general notes and see if you might still have grade B specified there and go ahead and switch that to grade C. So in addition to the elimination of grade A, ASTM 500 has a few other recent updates that you should be aware of as well. A big one of those is that the yield strengths were updated. So yield strengths for round HSS used to be slightly lower than yield strength for square and rectangles, and now they are the same. And since STI recommends using grade C, because you're getting that even if you don't specify it, then now your round grade C matches the rectangle, which is 50,000 KSI. So you should and can be using 50,000 KSI for your round HSS shapes. Another change was made that the maximum wall thickness was increased from 7/8 of an inch to 1 inch, and the max periphery was increased to 88 inches. That means we will see larger HSS shapes available domestically here in the US. Our largest square shape doesn't change. That's still an HSS 22 by 22, but we can now specify up to 28 inches round, and rectangle shapes have increased up to 34 inches by 10 inches. We'll have a slide on this later on in the presentation as well. Our STI Manual Volume 1, which is a free download on the website, has tabulated section properties. Those do reflect the larger HSS section, and our HSS Connect software has the larger sections and the higher yields as well. So the next thing we want to talk about in materials is non-structural and other structural ASTMs. So let's talk about A500 round HSS a little bit more for a minute and take a look at A53, which is sometimes specified as an alternative to A500. A53 is the spec for black lacquer coated welded and seamless steel pipe. It's intended for mechanical and pressurized water applications. We don't recommend that you use that. We recommend that you specify A500 rounds and don't specify A53. The reasons for that is that the A53 minimum yield is either 30 or 35 KSI, so lower yields than you're getting for A500, significantly less than 50 KSI for sure. And it's more expensive. It has to go through testing to make sure that it can handle the pressures that it's intended for, so that testing makes it more expensive. It's also coated, as I mentioned a second ago, so you're paying for that as well. And then if you need to weld to the pipe, then you have to remove that coat, and that comes at an added cost also. So we don't recommend that you specify A53 for rounds. Go ahead and specify A500 for your round shapes. If you are asked to substitute A53 for A500, go ahead and check that minimum yield, because it is lower, as I just mentioned. And if you're designing to 50 KSI and you get a request for a different ASTM, then you need to make sure that it meets that yield. The other spec that I have listed up here right now is A513. That is a spec typically used for small tube sections with very thin walls. It's also intended for mechanical applications. It doesn't have any yield requirements. So if it does get spec'd, you do need to make sure that you are obtaining steel with the minimum yield that you're requiring on your project. You can get it with a certain yield strength, but you have to double check and make sure that you're getting that in your certifications. So just to recap all of that, we recommend using A500 for all structural applications, round and rectangular. We don't recommend that you specify A53 or A513. They are not intended to be used for structural. In most cases, their yield strength is lower, and in most cases, they're more expensive. A1085, which we'll talk about here again in a second, is another tube spec. It did not become as widely available as we anticipated, so we recommend that you do check the availability before you specify it. You can use SDA's capability tool, which is on our website and lets you know which shapes are being produced regularly, and make sure that you can obtain that before you specify it in your projects. Our next topic is wall thickness for design. When you are using A500, which as we just noted is the most commonly used spec for HSS sections, you're required to reduce the wall thickness for design purposes to 0.3 times the nominal wall thickness. This has been in the spec since 1997. That 0.93 signifies a reduction to the nominal wall thickness due to the tolerances that A500 allows, which is up to plus or minus 10%. So because you could have that large swing in wall thickness plus or minus 10%, the code added this 0.93 factor to the nominal wall thickness to adjust for that. Now, if you are pulling properties from the manual, it has already included that 0.93 in its section property tables. So you should see a T design and a T nominal. So if you're pulling from those tables, it's already included. Also, it's included in the area calculations, all of the section properties that are already in those tables. Now, if you do end up using A1085, don't reduce the wall thickness for that. A1085 has different tolerance requirements, and they are more stringent, and so this reduction is not required, and the full nominal thickness is used in design calculations. The STI Design Manual Volume 1, which is tabulated properties for all tubes across A500 and A, reflects the differences in these tubes and their materials. That Volume 1 is available as a free download on our website. So if you're pulling from tables in AISC, you're using A500, you can always go to tables on the STI document to get section properties that have been calculated for both sets of ASTM specs. Now let's talk about choosing wall thickness in your design. We need to remember connections when we're performing HSS member design. If there's one thing that you hear over and over in SDI presentations, this is it. Don't assume that lightest equals the cheapest with HSS. Due to the flexibility of the HSS walls, which we're connecting to, local strength at those flexible HSS walls may control. Don't be fooled if you're looking at tension-only designs. For tension-only loading, the slenderness ratio will likely be very high. You'll probably have a very thin wall. But for the joint connection, it's recommended that the slenderness ratio be kept as small as possible to help minimize fabrication costs when you get down into into connections. So consider that wall thickness up front and make sure that you don't end up having to reinforce your connections down the line. If you understand that in the first phase of your design, that'll mean more efficient and economical connections. And that's because fabrication costs are going to factor heavily into that finished structure cost. That flexible wall that we just saw, that is one of the ways that a HSS can fail, and that is called a limit state. So anyone new to designing structural steel connections involving HSS members might be surprised or a bit overwhelmed by the various limit state equations listed in the AISC steel spec tables. Within Chapter K, that are unique to HSS. They include punching, local yielding, local buckling, plastification. We'll take a look at those on the next slide as well. This would also be something that you would have to consider if you were connecting to the web of a wide flange, and that's covered in a different part of the spec, and we will touch on that, how they're combining these two applications in the 2016 code and forward. So 2016 did remove many of the prescriptive connection design tables that were in 2010 Chapter K. So make sure that you're not using these outdated Chapter K tables. What we recommend that you do instead, of course, if you're designing to the 2016 code, then we recommend that you use STI's limit state tables. They are what we call a cheat sheet or a roadmap for HSS connection design to make sure that you're not missing a limit state check and using the correct equation for AISC 360-2016. We have limit state tables for shear, axial, truss, and moment HSS connections. This is another free download from the STI website. So we want to make sure that we're moving away from some of the outdated tables and moving toward the current requirements. And so that limit state table is an excellent tool for that. And then just a heads up, don't assume that your connection software is checking all limit states until you verify that. There are many limit states that apply to many HSS connections, and some of the more obvious ones are checked by software, but there may be one or two that are not. So we recommend that you verify that before you move forward with assuming that your connection software has checked all of the limit states. To reiterate and sum up what we just discussed, we're going from the 2010 Chapter K, which is the table or the chapter that deals with HSS sections. We're going from many tables that were very prescriptive, that were unique to the specification and not found for any other shapes. The content was therefore repetitive, and it required limits of applicability to make sure that you were using these equations correctly. And instead, we've gone to a Chapter K that is more streamlined. It adds on to Chapter J, which was that requirement for the web of the wide flange. It's more consistent in that way because there's no duplication of formulas, and we removed many limits of applicability. So now these equations can be used throughout any situation and not just in the few conditions where the limits of applicability were met. To help you understand visually those limit states, on the left you see an example of shear yielding, which is also known as punching, that can occur in both tension and compression when you're connecting to the face of your HSS section. The image to the right is plastification, and that flexible tube wall is deforming. We also have sidewall failure, which can be yielding, crippling, or buckling. And then lastly, we can have local yielding with some uneven load distribution if the cord member is more stiff than the branch member connecting in. You can see premature failure of the branch member due to that uneven stiffness. So these are just a few of the limit states that you have to check when you're designing HSS connections. And then moving into limits of applicability, although these have been somewhat removed from the code in trying to keep things more in line with Chapter J, there still are some limits of applicability that you need to become familiar with. These govern the use of the prescriptive AISC equations. So you need to check and make sure you fall within those limits if you're using the prescriptive equations that are still in the code. And then don't apply those prescriptive equations if the connection falls outside of the limits of applicability. An example of this would be in AISC 36016, section K3, if you're looking at HSS truss connections. When the truss branches are welded to the cord and your joint eccentricity is within the limits of applicability, then the moments that result from that eccentricity can be ignored. So that's just one of those limits of applicability that come into play when you're looking at connections for HSS members. A specific limit of applicability is end distance. And when a connection is near the end of an HSS member, there may not be adequate length to develop a traditional yield line pattern. So do be aware that the connection available strength per Chapter K must meet a certain end distance limit of applicability. And you can see a couple of the equations listed here. Those aren't all of them. But for round and rectangular shapes, you must meet a certain end distance in order to achieve the full connection strength in the equation. If you don't meet that end distance, then you do need to apply a reduction where that limit of applicability is not met. And the commentary in 2016 states that a conservative reduction of 50% can be taken. If you don't want to reduce your connection strength by 50%, you could always use an end or a cap plate to waive that end distance limit of applicability. This connection does not meet the end distance requirements. You can see this is some testing that's been going on that's being done by Dr. Packer. And in this case, we are not going to be meeting that limit of applicability. So options here would be either to reduce the capacity by 50% or put a cap or an end plate there. I guess in this case, it would be an end plate. We saw that flexible wall in the HSS connection, and the flexibility of that wall results in this effective width phenomenon for rectangular HSS sections. As you can see in this image here and kind of picture, the wall, the face of the HSS that spans between the side walls is going to be stiffer where it's connected and more flexible in the center. So that causes a non-uniform distribution of forces. So in many instances, you can't rely on the full width of anything connected to that face. Now, the code is very specific about this is for connection of plates or branch members that are perpendicular to the longitudinal HSS axis. And in those situations, there is a formula to calculate the effective width. So the full width is not going to be effective. You have a reduced width that is effective. And that is in the equation K1-1 that's shown here. So once you've calculated that effective width, you do have to use that to calculate other reduced parameters. For example, if you have a weld along a transverse plate that is transverse to the longitudinal axis of your HSS, you have to use an effective weld length. You cannot use the full length of your weld. So this is an equation in table K5.1 that's listed here as to how you would calculate the effective weld length. Because again, graphically, you can see there that the force in your weld is going to be higher towards the sides where it's stiffer and lower in the middle. If your element and your weld are parallel to the longitudinal axis of the member, it's considered fully effective, as an aside. So a little bit more then about welding to HSS. There is a pretty commonly used directionality factor of 1.5 that's applied for fillet welds. And you need to apply that directionality factor correctly for HSS, which means that in most cases, you don't get to use that 1.5 increase for most HSS. We will go through this a little bit, the reasoning why, in the next few slides. This is a nice rule of thumb to be aware of, not related to the directionality factor, but welding to HSS. If you're trying to develop the yield strength of a branch member, a fillet weld of 1.1 times the thickness of the branch member if it's a round branch, or 1.3 times the thickness of a branch member if it's a rectangular branch, will develop the yield strength of a branch member. Just a nice little tip to be aware of there. And another specification, a limitation in this case that does not need to be applied to several HSS applications, is when you have a maximum fillet of the thickness of your material minus 1/16 inch required. This is in J2.2b, and we'll look at this again in a little more detail on the next few slides, but that limitation does not apply to HSS at base plates, and we'll talk about why here in a second. So going back to this directionality factor, let's look at that a little more closely. Section J 2.4b permits the use of directional strength increase factor, and that gradually increases from 0 if it's a longitudinally loaded weld to 90 if it's a transversely loaded weld. I'm sorry. It increases from 0 for a longitudinally loaded weld to 1.5 for a transversely loaded weld, which is a 90-degree angle. And that's where that angle comes into play in the equation there. So we see that as something that's allowed, that 1.5 increase. That was based on research for lap slice connections loaded in shear. When we take a look at welds on HSSs, oftentimes we are not welding to both sides. You don't have access to the inside of your tube, so your weld is just on the outside, as you would typically see when you're welding an HSS to a base plate. That means that you're getting a single-sided weld, and that load is eccentrically loading your weld. And that is going to make that weld prone to bending about the local axis. It's going to induce some moment, and it's going to open up the weld root. So because of that, the restraint that was provided was not what had been assumed in this original 1.5 increase. That restraint actually varied depending on the HSS wall thickness, the shape, the weld size, the penetration. It turns out that this effect was much more severe on rectangles than rounds, and the decision that was made is that a 1.5 increase should not be used for rectangular HSS in tension to base or cap plates. However, it is okay for round HSS. And that the 1.5 increase should not be used for transverse plate to HSS connections. That would end up being a rectangular HSS because you're not welding a transverse plate to a round. It is, however, permitted for double-sided fillet welds. So in summary, you can use the 1.5 for a round HSS in tension. Don't use the 1.5 increase for a rectangular HSS in tension. The other welding limitation that I had touched on in that first slide in this section was a limitation on the size of the weld applied to the edges of your member. This was a limitation because, as you can see in this illustration on the bottom, that weld could melt away the very top edge of a member that you were connecting. So a reduction is given of 1/16 to account for that and to make sure that you are able to develop the full weld throat. So that is not applicable for an HSS base plate. If you see the image here, and you can picture that, your weld is not along the edge of the thickness of your HSS. It's along the side. So it does not need to apply here. You can go ahead and use that max fillet weld up to the thickness of your wall. So don't apply this limitation to HSS at a base plate. The other type of connection we want to address is bolting to HSS. And bolting to HSS can be difficult. Just like you can't get your weld to the inside of a closed section, it's also going to be difficult to access that inside of the closed section to get to the bolt as you're trying to tighten that. So due to that being a closed shape, bolting can be difficult. Not impossible, but it can be difficult. If you are using traditional bolts, don't forget that you're going to need to specify access holes, unless you're fortunate enough to be able to reach in from the end of your tube. If you're not using traditional bolts, but you're using through bolts, we recommend that you don't do that if at all possible. They are difficult to install. Once you get through the entire center of your HSS, the required length for that, plus your nut and all of the other required distances that go along with that, may exceed typical bolt stock. If you are tightening down with a through bolt, then don't over tighten it. That will distort the walls of your HSS. So you can only bolt snug tight if you're doing a through bolt, unless you reinforce your HSS. So if you are using through bolts and you are tensioning them, then you do need to reinforce that inside cavity of the HSS in some way. Alternatives to through bolts and traditional bolts would include Nelson studs, which are welded on, or blind bolts, which come through a variety of manufacturers. A look at through bolting. Again, on the left, you see how you would want to do through bolting. You would want to install this reinforcement or sleeve inside the hollow section so that the distortion of the walls that you see on the right does not occur. So we do want this to happen on the left. We don't want this to happen on the right. And then this is just an image that a previous colleague of mine took of her trailer hitch on her vehicle. And you can see sometimes it's difficult even to get a little bolt through that small HSS section. You can imagine what it would be like to get a through bolt installed during construction up on a scaffolding somewhere and trying to get that all to fit through all those plies. Okay, so truss type connections. When we talk about truss type connections, we're talking about cords with web members, and they're usually attached to each other. Don't necessarily have to be in a truss, but they typically are. So when you are designating your truss type connection, the way that you design for it is based on the connection type, and that needs to be designated based on the actual transfer of forces in your connection. Don't designate your truss connection based solely on what it looks like. Don't assume that just because it looks like a K, it is a K. And here is a slide that shows you some of those truss type connections that are very typical with HSS sections. So some of those include K, which also includes N. Those are loads that are equilibrated by other branch members on the same side of your cord. Y, which also includes T. Your load is equilibrated by beam shear in the cord member. And then X, or cross loads, that load is transferred through the cord member and equilibrated on the other side. So based on where the load goes is how your connection needs to be designated, and that tells you how you design for that connection. So 100% of the force within 20%, so there is a little bit of leeway given there, needs to fall into the type of connection in order to design to that type connection. And then our last sort of major do is that we do recommend that you use STI resources. We've talked a little bit about a few of these, and we will go into some more depth here on exactly what is available. But we have a ton of materials available for your use. The HSS design manuals, which include those tabulated HSS properties as well as worked through examples, limit state tables, the capability tool, which tells you which producers are making what shapes, the HSS Connect software, which allows you to check your wall thickness. You can get e-news delivered to your email. We have a resource library to search with webinars on demand and many, many articles that will help you as you are designing HSS connections. We don't always want to use old general notes, things that specify something like grade B or that all HSS members be through bolted. We want to make sure that we're updating to some of the newer data and research that's been made available and not just say, well, we've always done it this way. Those HSS design manuals are shown here. The Chapter 1 is a free download from our website for the electronic version. They are available both PDF and hardback, or not hardback, printed. It's a softback. They're available both PDF and printed, and you can purchase those on our website. The limit state tables that I talked about briefly, this is just a snippet from one. It's a little bit hard to show the whole thing because they are so jam-packed with information, but you can see the top couple of lines and columns here of this HSS to HSS trust type connection. These are some of those T and Y and cross connections that I had just talked about. And these limit state tables are an excellent resource for transitioning from 2010, when your limit state was possibly easier to find in a table, to 2016, where that limit state is more consistent with the rest of the code. And we are plugging HSS specific parameters into equations. It also lists out the limit states that are applicable to each type of connection. So this is a great resource to go and, like I said before, your cheat sheet as you start designing to make sure that you're hitting all of the limit states. The STI capability tool, this is so that you can know what is actually being manufactured out there. I know that your software is great for picking the lightest shape, and there are a lot of HSS shapes available, and you may wonder, well, what's common or what can I actually get? If you type in your shape here, your grade, and click Find Producer Capabilities, it'll tell you if that shape is regularly produced, which for this basic square it is, and who produces it, or it'll tell you if it's a hollow circle that it's only produced on demand or it's not produced at all. So this is a great tool also on the STI website for making sure that what you're wanting to use, what you're specifying is actually available. STI HSS Connects is a software on the STI website. The main point I made a while ago was that you need to consider your wall thickness for your connections up front in your member design. You may not be ready to step through the whole connection yet. You may even be delegating that down the road. But you probably know the force that's going to be required to be resisted at that connection, and you can quickly go into HSS Connects, plug in your parameters, and see if your wall thickness is going to be adequate. Now, this will not check your welds, your bolts, things like that, but it does check the wall of your HSS itself. And I'm excited to announce that HSS Connects used to only be available with professional membership, but now it is accessible by anyone. It's free for everyone to use. You just need to go to the STI website and register for it. So that brings us to our first polling question today. And that question, which will pop up on your screen here momentarily, I hope. I'm not seeing it on my end. The question is, the engineer is required to check only one limit state per HSS connection design, true or false. I see that now, so I hope that popped up for everyone else. The engineer is required to check only one limit state per HSS connection design. I'll just leave that up for a couple more seconds. And we'll go ahead and close that out. And the answer to that is false. The engineer must check all of the limit states that apply to the particular connection. Okay, so this next portion and final portion of the webinar today is big picture do's and don'ts. I'm sorry, Patty, were you going to tell me what the results of that were? I thought I heard someone break in. It's okay. I already gave the answer away.
It was 97% were false. So
awesome.
The answer was
great.
Was mainly false.
Yes, thank you very much. Okay, so moving into big picture do's and don'ts. We at STI often hear that designers don't specify HSS because it's too expensive. We think that's like saying, well, I'm going to use a pencil and a straight edge because the computer is too expensive. It's about how you use the capabilities and efficiencies to know if it's worth the cost. So we want to focus on how HSS is beneficial in the big picture of steel construction. There are a lot of benefits. It's excellent for columns, and the biaxial strength makes corner columns using HSS a must. It has torsional superiority to open sections. It is great for curved members, for exposed members, and we see it used a lot in unique and non-building structures. So don't default to the idea that HSS is expensive. It does have an efficient weight to strength ratio. Sometimes when comparing wide flange per pound to HSS per pound, wide flange will be less expensive depending on the market values because it all fluctuates. But HSS is more efficient per pound for axial loading. So we need to look at that overall fabricated project cost, not just the dollars per ton. Especially in columns, we want you to use HSS columns. They are more efficient than wide flange columns in that there is no weak axis. So bracing is not going to be an issue as much. Here's a specific example here for a 12-inch tall column. If you were using a W12 by 58 or an HSS 12 by 12 by 3/8, which are basically the same weight per foot, the HSS has 12% more capacity. We can also fill the HSS with concrete for extra capacity. And as we mentioned a little bit earlier, we now have some jumbo HSS sections that are further going to increase our capacity. Squares up to 22 inches and rounds up to 28 inches, but rectangular sections can now be 34 by 10, and the walls can be 1 inch thick. So that's going to increase our capacity as well. You see this used a lot in big box and warehouse type stores. This is a Target store here. You want as much open floor plan as possible. You want to spread out your columns as much as possible, so you want to make them very efficient. Also, it's nice to use closed shapes because they stay cleaner. You don't get dust and buildup inside like you would with an open section. We want to use HSS to reduce bracing. This is an instance where that biaxial strength comes into play. There's no weak axis. This vertical truss that you see here was a case study that we did, and we saw that the original design was for the chords of that vertical truss to be wide flange, and then the web members to be either single or double angled. And we thought we might be able to reduce that if we looked at those all as HSS members. And what we saw was that if you used HSS for both the chords and the web members, we were able to reduce the quantity of web members. This was primarily because we didn't get hit by the weak axis of a wide flange chord and didn't require bracing as often. And by getting rid of the web members, we reduced material, we reduced the number of connections, and then the overall cost. You can see some numbers there. We went from 174 kips down to 114 kips, 81 pieces to 49 pieces, and that resulted in a 34% weight savings. Another place HSS are used in the big picture are in curved and architecturally exposed structural steel. Of course, go ahead and curve HSS. They can be bent or rolled. You can use cold or hot processes, and round HSS are especially adaptable to almost anything a designer can. That's supposed to say either imagine, but I guess image works as well. Go ahead and expose HSS. Their smooth appearance is very pleasing. As you can imagine, architects like the clean lines of HSS. You have a variety of shapes to expose. And I wanted to point out that not all exposed HSS needs to be spec'd as AESS. You can still get that nice clean look and not necessarily incur any additional costs. This is a structure called Allianz Field. It's the Minnesota soccer team. It was a AISC 2022 Ideas 2 award winner. It has a transparent building skin. It's supported by round 18-inch diameter HSS, and they were chosen both for their appearance, but even more importantly, their ability to resist the large loads imposed by the skin. So these HSS drive the skin's geometry and create the supporting structure, and that gives it its distinctive form. You can read more about this project. On the STI website, we published an interview with Justin Barton, the principal and senior project manager at Walter P. Moore, and the architect for that was Populous. This is a few pictures of that under construction. It had that complex geometry. Each HSS piece was curved in single curvature, although every radius varied, and they connected them with these big end plate moment connections. And this created a complex look, but it allowed a very straightforward fabrication and construction process. And those end plates were designed to take the bending, the gravity, and the axial loads. HSS are often used for exposed exterior curtain walls. This is the SeaTac International Airport, and we're all familiar with this. When you're wanting to let in light, exposed HSS are great because they look nice without blocking that light with unnecessary enclosures. And another image here, this is the Salvador Dali Museum in St. Pete, Florida. And in this case, rectangular HSS were used. This is a space frame supporting a freeform glazing system. Multi-story columns, especially such as this one in canopies, are excellent uses for HSS. They are unbraced their entire length. And I believe this was a 26-foot roof cantilever here. So the roofing members were also HSS. And we incorporated, not we were not the ones who used, who designed the project, but the designers incorporated cast connects forged steel castings so that they had a taper and pin connection at the top and bottom of each column, which was a very neat final look as well. HSS are used as part of canopies. This is back to Allianz Field, and the compression elements of this cantilevered canopy are HSS sections. You can see that in the column and the braces there. Another application where you want to let light in without blocking it is atriums, and this is the Transbay Transit Center. It used HSS, again with casted connections, for a seamless final look. HSS are often used in non-building structures. They're so flexible and can take on many, many unique shapes that in this instance, which was the Ballston Quarter pedestrian walkway in Arlington, Virginia, this pedestrian bridge needed to connect two buildings that were offset. So they created this very unique twist in the middle. This was a really interesting project. Not only does it twist, it's supported at the center and the sides cantilever, and that HSS frame maintained the necessary rigidity to minimize deflection and bounce for the pedestrians who were walking across that walkway. And of course, it just looks cool. And HSS is not just used in exterior curtain walls, it's also used for architectural and visual elements on interiors as well. This is the Brookfield Place Entry Pavilion in New York. This was another one of the AISC Ideas 2 award winners from several years ago. So that brings us to our summary table. I don't expect you to really read all of this right now, but I wanted to take all of the do's and don'ts that we've covered in the presentation today and put them in one easily accessible place so that you can take a look at this as you are utilizing HSS in your next project and want to refer back to some good things to remember. So with that, we have our final polling question, which is simply to ask if you would like a PDH certificate for attending this webinar. And I'll go ahead and let you take a few seconds to answer that. Remember, you need to answer yes if you want an actual certificate to be sent to you. If you're self-reporting and you don't require it, that's fine. But please answer yes if you would like that certificate sent to you. And again, I'm getting a little bit of a delay on my end, so I'm just going to wait a couple seconds longer and make sure that we've all had a chance to answer that. Okay, so we'll go ahead and close that down. I promise we're getting to Q&A here very shortly. If you enjoyed this webinar, STI has several more upcoming webinars that you can see listed here. We have one on October 5th, November 9th, and December 7th to round out our series for the year. So with that, I am happy to take some questions. I have a colleague on the line with me as well to help answer those, Kathleen Jacinto, who is another structural engineer.
Good afternoon, everyone. Oh, sorry.
I'm going to flip back to the summary slide while we go through these, unless I need to go to a specific slide.
Sounds good. Thank you, Beth. I hope that everybody can hear me. My name is Kathleen Jacinto, and I'll go through the questions that have come in and do my best to capture all of them. We may go past the hour mark, and please feel free to stay on if you would like to continue to hear all the questions. I'd like to go through as many of them as we've received, or feel free to log off as you need to. So the first question that I'll go through for our Q&A is on slide page 15. Why is it that the wall thickness is reduced to 0.93? Oh, it might be 17 on or 13 on yours. Why is it that the wall thickness is reduced to 0.93, the nominal thickness? So we need to reduce the wall thickness for HSS when we specify ASTM A500 steel. So for that specific specification, when you dig in and open up the ASTM A500 document, you'll find that A500 HSS sections, they can be produced and manufactured with a wall thickness of plus or minus 10% of the nominal thickness. So basically, the HSS that you'll receive on site for A500 could potentially have a smaller wall thickness than the nominal wall thickness for up to 10% less than nominal. So you may not get a 3/8 inch thick wall, you'll get something up to 10% less than that. So when we're designing HSS, we need to account for that, for the potential for that smaller than nominal wall thickness. And it was decided that we would take a 7% reduction on wall thickness, or 0.93 times that nominal thickness. Follow-up question to that is, are the unit weights based on 0.93 nominal T or the full nominal thickness? So in the AISC manual, or in our STI volume 1 manual, which shows all section properties for HSS, the unit weights are based on the nominal thickness. So the full thickness of the HSS section. So the weight is based on full thickness. And just to note that the title of that column is called nominal weight to help to clarify that. Another follow-up question is, are those thickness adjustments already accounted for in the blue steel AISC manual? So that might be the more recent 2016 AISC specification or 15th edition manual. So yes, the 7% reduction has already been accounted for when you look at the specific section properties, such as section modulus, not the weight. As I just mentioned, it is not, we consider full nominal thickness for weight, but for section properties in the table, they do already include a reduction on wall thickness. So it already considers 0.93 times T for HSS sections in the manual. However, when we are designing connections to HSS sections, we need to make sure that we're using the 0.93 times the nominal thickness. So when you look at the T column in the manual, it will already have been reduced there. The design thickness is already 0.93 times T, and that's what you should be using for connection design. The next question that came in is, I'd like to verify that round HSS A500 grade C, so this is going maybe to the A5, to the specification slide, where we talk about, the question is verifying that round HSS A500 grade C is always 50 KSI. The AISC table 2-4 indicates preferred material specification is 46 KSI. This is a great question, and happy to clarify this, that yes, the current ASTM A500 grade C is a minimum yield strength of 50 KSI. So confirming that yes, this slide is correct, the current ASTM grade C is 50. This ASTM A500 document was updated in 2021. However, the latest AISC, our current 15th edition manual, that was released in 2016. So that had the previous ASTM numbers in that edition. So that's why when you open the 15th edition manual released in 2016, that North Carolina Blue manual, that table 2-4 shows a grade B of, or it shows the round HSS grade B of 46 KSI, which that was created prior to the 2021 ASTM update. The next edition of the AISC manual that will be released this year, later this year in 2022, the 16th edition, that will be revised to reflect the latest ASTM A500 updates. Also on this note, if we could go back to the slide that compares A53 to A513, I just wanted to add here that yes, we do recommend specifying A500 round HSS over instead of A53 or A513 for structural applications. However, there are instances where it does definitely make sense to specify A53 pipes or A513 smaller structural sections. For example, A513 is often specified for handrails or secondary components that are not taking heavy structural gravity or lateral loading, but it does make sense to specify that smaller thickness for any secondary steel that you're specifying on a project. So it's okay to specify A53 and A513. There's specific applications where they do make sense. Our point is that we just want to make sure that you're specifying a minimum yield to match what you've designed. And we also are releasing an article now to help in guiding that specification when you do want to specify A53 or A513, how to best specify those. I just wanted to add that clarification here while we're talking about material specs. And going on to the next question, on slide 16, which might be your 14. Oh, no, try yes, this one, thank you. On slide 16, it says per that bottom note, per AISC 360-16 K2.3, the available strength of connections to rectangular HSS with concentrated loads shall be determined based on the applicable limit states from Chapter J. However, on slide 17, the next slide, it shows a connection with concentrated load and limit states, shear yielding and plastification. These two limit states are not in Chapter J, which has different limit states such as web local yielding, web local crippling, etc. Could you please clarify? So the answer to that is in the latest edition of the AISC specification, the 2016 version, Chapter J, there is a new section, section 10, the very last section of Chapter J. That is called transverse forces on plate elements. So that was newly introduced in the 2016 spec, and that section points you to the 15th edition manual, part 9. When you go into that manual, part 9, I can even share the page. It's manual page 9-14. That's where you will find the limit states for punching and plastification. So there's a little bit of a roadmap to follow, but it does get, the specification does get you to those two limit states that were referenced on that slide 17. And to help in navigating this, we know that there's a lot of limit states to check, and knowing where to find them does take a little bit of navigation. I do highly recommend looking at STI's limit state tables that list all the limit states to check for HSS connections and where to find them in both the 2010 spec, the older spec, and then the current 2016 spec. So here, what Beth has brought up on the screen will, on the left, you'll see the limit state, and then on the right in blue, it shows where to find those equations in the 2016 manual, AISC manual.
Yeah, and I want to point out that we have additional pages, not just this one. So the ones that have like a similar transverse plate connection are available. They're just not shown here.
Yes, thank you, Beth. Okay. And another question is, where do we find the limit state table? What we had referenced as a cheat sheet on another slide. So they are on the STI website. It is free to download, and we have placed links to the specific documents in the chat for this webinar. But it can all be found on the website. When you go jump in next to the STI website, under the resources tab, there's a resource library where you can search for limit state tables, or under the products tab, on the left, you'll see HSS, and there's another site pointing to the to HSS resources, where you can find many HSS specific resources. Okay, let's see. We have some newer questions. Let me see if I can. Another question that we received is, are there common details available on your website for exposed HSS and how to handle potential water intrusion? So off the top of my head, I know that we did give a webinar on AESS. AESS stands for Architecturally Exposed Structural Steel. And we did give a webinar last year, 2021. All of our webinars, we have free recordings for our webinars that can be found also on the STI website. We call them webinars on demand, but we did present some guidance on how to detail weep holes for HSS. And I believe we also have an article on our website specific to weep holes and water infiltration. I can also email the individual that had asked this to try to give more guidance on where to find these resources. But we don't have a set of like a library of details to offer, but we have an article and webinars that we discuss and provide details there. Okay. Another question is, what is meant by do not use the 1.5 strength increase for fillet welds for transverse plates to HSS? Okay, so so just to clarify, the 1.5 strength increase is the directionality factor per AISC Chapter J 2.4, where if you have a load that is applied transverse to the weld, then for certain applications you can increase your capacity of your weld by up to 1.5 using this KDS factor shown on this slide 24. But however, we want to clarify that this cannot be used for all applications. That for one instance that we cannot use it for HSS is if we have, say, an HSS column, and if you have flange plates connecting into with a wide flange beam, and you have flange plates at the top and bottom of your wide flange beam, and you're connecting transversely to that HSS column, we cannot apply we cannot apply that 1.5 increase. So that transverse plate connection, which would be at the top and bottom flanges of a wide flange, for instance, that it's perpendicular to the longitudinal axis of your HSS column, that type of connection, we cannot apply a 1.5 strength increase. That weld directionality, we cannot apply the weld directionality factor per Chapter J 2.4. Let's see. I think that we may, I don't know, Beth, if you're also seeing questions. There's a lot of good questions, which is great to see.
I don't see them. They don't come through to me.
No problem. I was just wondering if you saw any that you
what I think we should do is maybe take one or two more, and then if we didn't get to the question, then we will follow up via email.
Yes, agree. So here's another question that I think was asked twice, so I'll cover this one. Is A1085 no longer being pushed to replace A500? This is an excellent question. Okay, just a moment, let me make sure. So ASTM A1085 is currently being domestically produced by HSS producers. And just in case not all on this call today understands the process for distribution of HSS, HSS is produced by HSS producers, and then they are brought into service centers. Service centers they're stocked in service centers and stored and then distributed from there. So even though A1085 is produced by HSS producers, not all service centers stock A1085. So if you need A1085 for your project, it is best to check with a producer to ensure that the shape that you are specifying is available. We are more than happy to help in trying to get A1085 material for your project if that is what you would like to use. There is essentially an availability and that we can't guarantee for your project. So it's always good to check in advance before specifying it to ensure that the number of ASTM 81085 sections you need and the specific section and shape you're looking for is stocked in service centers for distribution. So I think there are more questions that we did receive, and we thank everybody for submitting your question, for joining the call today, and we will go through each one and respond via email. But we hope that we were able to respond to at least a few of these questions that have come in, and we thank you for joining. And Beth, I'll hand it off to you.
Okay, yes, we appreciate your staying through, and if you do come up with any additional questions, feel free to email us to hssinfo@steeltubeinstitute.org. That's how we obtained all the do's and don'ts for this webinar and how we hope to continue answering questions for everyone as they move forward with their HSS projects. So with that, that will conclude our webinar. Thank you, everyone, and have a good afternoon.